Hello, welcome to Math 121 Final Exam Review for Doniana Community College. I've broken this into 4 parts. The first part is going to be linear and quadratic functions, and if you have a copy of the review, the questions are 2, 3, 6, 7, 8, and 15, although some of them are similar, like 2 and 3 and 6 and 7 kind of go together, so I only did one of each of those just as a model. If you do not have access to this particular review because you don't go to DACC, I'll put a link in the description so you can have access to this worksheet as well. All right, so our first question, let g of x equal 5 and then parentheses x minus 23 squared minus 2. This comes from our section in the book called Quadratic Functions, Chapter 3. In Part A, give the coordinates of the vertex. Okay, so we know that vertex form is given by f of x equals a times x minus h all squared plus k, with the vertex at hk. Now notice the vertex form has a subtraction inside the parentheses, so that's standard. And it has addition outside the parentheses after the squared. So it's a vertical shift, and inside it's going to be a horizontal shift. Notice the standard form has minus and then plus. And the vertex is hk. So if we look at our formula up here, x minus 23. So we're subtracting, so that's standard form. So 23 is the value of the x coordinate. And on the outside, it says minus 20. Standard form is plus k. So this is plus a negative 20, which tells us our y-coordinate is a negative 20. All right. Explain how g of x is transformed from the graph of y equals x squared. And if we highlight them here in various colors, the 5 out in front, because it's in front of the squared, it's before the operation of the function itself. We call it on the outside, and anything affecting the outside of the square is going to refer to the vertical. So for multiplying, we're going to have a vertical stretch by a factor of 5 units. The x minus 23 should have been highlighted in red. Somehow I forgot to do that. This is a horizontal because it's directly affecting the x. It's inside of the square, it's right next to the x. So it's going to be horizontal. And it's a shift of 23 units, and it goes to the right. And if we wanted to solve for this, to figure out how that works out, let's see if I could do this here. We could take x minus 23. It's not planned here with a little mouse. Set it equal to 0, and we find that x equals 23. This will give us not only our coordinates of the vertex, and not only our shifting of right or left 23 units, but this will also give us the axis of symmetry. If we ever need to find the axis of symmetry, it'll give us the axis of symmetry as well. All right, and the vertical shift 20 units down here in green, it's on the outside. Adding or subtracting, we're going to go either right or left or up or down. Since it's on the outside, we're going to go down. On the inside, right or left, outside, up or down, outside. So when we multiply, it's going to be a vertical stretch or compression. All right, next slide. What are the zeros of g of x? The zeros require some work, but the question itself, this is a lot like Jeopardy, the question tells you exactly what to do. The zeros of g of x translates literally as zeros equal g of x. So I'm going to replace my g of x up here with a 0. 0 equals 5 times x minus 23 squared minus 20. Our general steps will be to isolate the squared part, isolate the absolute value, isolate the log, isolate the exponential, isolate the variable. We always start with an isolation of some sort. So let's add 20 to both sides. We'll have 20 equals 5 times x minus 23 squared. Divide both sides by 5. When we divide the right by 5, we have x minus 23 squared. When we divide the left side by 5, we have 4. Now that we have the squared part isolated, we could use the square root property. And I'll talk a little bit more about the square root property in a couple of slides. So when we take the square root of the left-hand side, remember, since we chose to take the square root, we have to add the plus or minus. So we have the plus or minus the square root of 4 equals, and when we take the square root of the right side, the square root of the square, we're left with the x minus 23 here. I like to take a step to simplify before I go on. So square root of 4 we know is 2, so plus or minus the square root of 4 is plus or minus 2, equals x minus 23. We have plus or minus, that's two equations. So I'm going to solve with positive 2. If 2 equals x minus 23, we can add 23 to both sides to get x equals 25. And if minus 2 equals x minus 23, we could add 23 to both sides to get x equals 21. We found the zeros. The zeros occur at x equals 21 and x equals 25. If we wanted to put these in point form, remember we started with y as zeros. So that would be 25, 0 and 21, 0 written as points. All right, number 6 has multiple parts to it. And I think I did most of these parts. I think I did all of them, actually. So solve using the most appropriate method. We'll talk about a couple of different methods here, 3 different methods. When given 4x squared plus 2x plus 1 equals 0, I would use the quadratic formula. I look at it and I don't think I see really anything that factors quickly, easily, something obvious. So I go to the quadratic formula. And the quadratic formula states the solutions to ax squared plus bx plus c equals 0 are given by our formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So I chose to put the b values in purple, a values in green, and c values in blue. When we look at our equation here, let me get a highlighter. The 4x squared, a equals 4. 2x, the coefficient of x, that's our b value, is 2. And our c value is the constant. The constant is 1. Okay, so using those colors, substituting in the formula, we have x equals negative 2 plus or minus the square root of 2 squared minus 4 times 2 times 1 all over 2 times 4. Now we're going to simplify this radicand, the thing inside the radical, first. So 2 squared is 4. We have 4 times 4 is 16. 16 times 1 is 16. So that's 4 minus 16, which gives us a negative 12. So we have x equals negative 2 plus or minus the square root of negative 12 over 8. We always simplify our radical first. Now the negative under the radical tells us we're going to have a complex number with the I. So the I comes outside of the radical, the square root of negative 1. 12 is the same as 4 times 3. And I use 4 times 3 because 4 is a perfect square. We know the square root of 4 is 2. We know the square root of 3 is not a number that we have any clue really what it is. If you memorized it, that's awesome. But we'll just call it square root of 3 because that's the exact number. So we've simplified our radical, the square root of negative 12, into 2i square root of 3. Still have the negative 2, still have the plus or minus, still over 8. So after we have our radical simplified, now we can simplify our fraction. And a lot of times it's easiest just to split it here at the plus or minus. Don't forget that that negative 2 is over 8, but also the 2i square root of 3 is over 8. So if you write them as separate fractions, it's sometimes a little easier to cancel. The 2 over 8 simplifies to 1/4. Again, 2 over 8 simplifies to 1i square root of 3 over 4, but we're far too lazy to write the 1 in front of the I. Minus 2x squared plus 4x minus 8. Solve using the most appropriate method. Now that I'm looking at this, I probably would have divided through by a negative 2 and reevaluated. But I decided just to go for the quadratic formula because I don't like trying to factor when there's a negative in front. Sure, I could factor out the negative, but then that opens me up to more possible errors. What if I forget to take a negative out of one of these two terms? So I'm just going to use the quadratic formula. And it turns out it's a good thing I did. Negative b, so it's a negative 4, plus or minus the square root of b squared, so 4 squared, minus 4 times negative 2 times negative 8, all over 2 multiplied by negative 2. appropriate substitutions. 4 squared is 16. Let me see, we have 3 negatives here, so we're going to have a subtraction. 4 times 2 is 8. 8 times 8 is 64. 16 minus 64 is a negative 48. Again, we simplify the radical. 48 is 16 times 3, so the square root of the negative 1 is the I. Square root of 16 is 4, and the square root of 3 stays as the square root of 3. We still have our negative 4 out in front, and it should be a negative 4 in the denominator. So this is an incorrect problem. Let's fix that. 2 times negative 2 is a negative 4. So we have negative 4 divided by negative 4, which is a positive 1. But when we have plus or minus a 4i squared root of 3 divided by a negative 4, the 4's cancel out. Plus divided by negative becomes negative. Negative divided by a negative becomes plus. And so since we have both options here when we're dividing by a positive or a negative, we still have the same options there. But my 1 was wrong. So I had to fix that because I don't want you studying the wrong thing and wondering, hey, Tuesday, where'd that come from? Part C, 7x squared equals a negative 28. Now, here's the square root method that I mentioned earlier. The square root method says, to solve an equation of the form x squared equals a, and a could be any algebraic expression, we could take the square root of both sides to obtain x equals plus or minus the square root of a. So in order to solve this, we're going to isolate the squared part. And I use this method, let me back up a minute. I use the square root method anytime I have a single term with a variable and it's squared. So in the previous ones, I had ax squared and bx. I couldn't really isolate the squared part because there was another x floating around. But here, there's only one x, it's squared, we can isolate it. So let's divide both sides by 7. We'll get x squared equals a negative 4. Square root property says I can take square root of both sides and get x equals plus or minus the square root of negative 4. Plus or minus stays. The square root of 4 is 2. The square root of the negative 1 is I. So the square root of negative 4 is 2i, and we'll have the plus or minus in front of it. We could simplify straight away if we only have one term that has the variable. Solve using the most appropriate method. Negative 24 equals x squared minus 11x. Anytime I see a quadratic, whether I use the quadratic formula or maybe not if I'm using the square root property, but factoring, using the quadratic formula, always first step, get it equal to 0. All right, set the quadratic equation equal to 0 so you can evaluate the best possible method. So 0 equals x squared minus 11x plus 24. I look at 24 and 11, and I realize that I could probably factor that. So I'm looking for all the values that multiply to be positive 24, and I write them down. To be positive 24, negative 1 and negative 24, also 1 and 24. Negative 2 and negative 12, also 2 and positive 12. Negative 3 and negative 8, also 3 and positive 8. Negative 4, negative 6, the positive options of both, right? Multiply to be positive 24. But the reason I only considered the negative ones is because not only do I want them to multiply to be 24, I want them to add our two numbers. I want them to add to be negative 11. So multiplying to be a positive, I know they have the same sign. If they add to be negative, I know the two numbers have to be negative, and that's why I only listed them in my little box here. So in all the pairs of negative numbers, multiplying to be 24, I see that negative 3 and negative 8 also add to be negative 11. Which tells me, using the zero factor property, states if a times b equals 0, then a equals 0 or b equals 0. Right? The only way you can multiply to get 0 is one of them had to be 0. Same's not true for 4. Right? Multiply two numbers to get 4. It could be 2 and 2. Right? There's no 4 there. But with 0, and that's why we always get it equal to 0, the zero factor property tells you exactly what to do. Get it equal to 0, then factor. And now we could use the property. So once I have my numbers, the negative 3 and the negative 8, I can rewrite my quadratic as 0 equals x minus 3 times x minus 8. These two binomials are multiplying to give us 0, so either x minus 3 is 0, in which case x equals 3, or x minus 8 is 0, in which case x equals 8. And the last attempt here, no, that's not true. The last part of number 6. 25 equals x squared minus 8x. We're going to use the same technique we did on the last problem. First step, we're going to subtract 25 from both sides to rewrite the equation, set equal to 0. And then I'm trying to decide, can I factor this? Well, multiplying to be a negative 25 can be a 1 in negative 25 or a negative 1 in 25. Multiplying to be negative 25, I could also have 5 times negative 5. But I want two numbers that multiply to be negative 25 and add to be negative 8. 1 in negative 25 add to be negative 24, and negative 1 in 25 add to be positive 24. 5 and negative 5 add to be 0. There's no pairs of numbers that can fit our properties. So when factoring doesn't work, if it doesn't come to you quickly and obviously, use the quadratic formula. Quadratic formula is awesome. Here our b is negative 8, so I make that substitution. My a value is 1, so I make that substitution. My c value is negative 25. Notice I use parentheses every time I substitute an a, b, or c. I do that so I don't lose these negatives. It's very important. So a negative 8 is 8. Negative 8 squared is 64. A negative 4 times 1 is negative 4 times negative 25 is a positive 100 over 2. 2 times 1 in our denominator. 8 plus or minus the square root of 164 over 2. I had to make sure that 164 was right. I checked it several times, so I'm going to keep hoping it's right. So 164 happens to be 4 times 41. 4 is the largest perfect square that goes into 164. It seems kind of small, but it's true. So we simplify our radical, rewrite 164 as 4 times 41. The square root of 4 is 2. The square root of 41, well, 41 is a prime number, so we're going to throw that inside the radical and leave it. Now we can simplify the fraction. We'll have 8 over 2 to give us the 4, plus or minus 2 square root of 41 over 2. The 2's cancel out and give us just the square root of 41. And I like it when I get an answer like this for the quadratic formula because it verifies, hey, there's no way I would have picked these two numbers up here in my multiply to be negative 25 and add to be negative 8. Never would have done it. All right, number 7, another word problem here. The cost function for a product is given by C of n equals n squared plus 12n plus 2100, where n is the number of units produced and sold, and C of n is the cost in dollars. All right, so what is the domain of this function in the context of the application? Well, we're making and selling products. So in the context of the application, n can't be negative. We can't produce a negative number of units of anything. So our domain is going to be 0 to infinity. Now that infinity is stretching it. We're not going to make an infinite number of units of this product. But we'll, better safe than sorry, we'll just give it that extension. Because we don't have any information that kind of slows us down and lets us know where production levels stop. Part B. Is the function one-to-one for the domain in part A? In general, a quadratic function is not one-to-one. But this is a restricted domain, so we should check, all right? Because we know a quadratic function with a positive leading coefficient is going to be a parabola opening up. So let's take a look at this. A quick examination of the location of the vertex, remember we could use x equals negative b over 2a, tells us the x-coordinate of the vertex is at negative 6. Why do we care about that? If we have our axes, and over here at negative 6 is our vertex, and I don't know how high it is, I don't know where it is, but I know a parabola opening up will look like this. And we don't really even care about this side because remember, all we care about is from 0 forward. And this part of our graph is one-to-one. All right? So in this restricted domain, our function is one-to-one. Part C, find the inverse of the function for the domain in part A. Show your work. And the hint is to use completing the square, so that's exactly what we use. Now, these variables represent specific things. C is the cost. N is the number of units. So we don't want to just switch those variables all willy-nilly. If this was just a regular f of x equals x squared plus 12x plus 2100, whatever, go for it, switch x and y. But we're going to do a modified version of the inverse that takes into account that the variables represent actual items or actual things. So we do not switch the c and n. We leave them as they are and solve for the, quote, other variable. Since c is isolated, our goal will be to get n by itself. So c equals n squared plus 12n plus 21. We're going to use completing the square. So I'm looking at the n squared plus 12n. And I want to rewrite this so it's a perfect square, so I could write it as a perfect square binomial. So I take half of 12, which is 6. I square it, 6 squared, added to both sides. That's a lazy 6. I add 6 squared to both sides. So on the left, I have c plus 36. On the right, now I've made it so this expression can be written as a perfect square binomial. All right, perfect square, as a binomial squared. Perfect squared trinomial turns into a binomial squared. N plus 6 squared plus 21 on the right-hand side. Now, if I want to truly solve for n, let's subtract the 2100 from both sides. 36 minus 2100 on the left will give us c minus 2064 equals n plus 6 squared. We have the square part isolated, so we take the square root of both sides, plus or minus the square root of c minus 2064 equals n plus 6. We're going to subtract 6 from both sides, but notice here I have plus or minus. Here I only have the positive version. You have to choose which one. In order to choose which one, what I did is I said, okay, a point on the original graph, when n is 0, c had to be 2100. Which means on the other graph, let's make that in blue, I had to have the point 2100, comma 0, because all an inverse does is switch inputs and outputs. So when I put 2100 in for c, 2100 minus 2064, I got 36. And I have a negative 6. I had plus or minus square root of 36. Square root of 36 is 6. I knew it had to be negative 6 plus 6 to give me the 0. The minus wouldn't work. That would give me a negative 12. So using a point from the beginning will help us choose, is it plus or is it minus, that we use in our inverse formula. So make sure you check that out. It's not always going to be positive that we keep. Using the inverse function from part C, which I have posted here at the top, we want to find how many units are produced and sold if the cost is $3,220. So we'll put in our 3220, subtract 2064, so we have 1,156 underneath the radical. That happens to be a perfect square. It's almost like this is a review problem and that was planned. Square root of 1156 is 34. 34 minus 6, 28 units should be produced and sold for a cost of $3,220. In general, if you have a problem that starts with words, you should give your answer in words. Right? If it starts in function notation, you answer in function notation. If it starts in words, you answer in words. All right. Number 15. The profit for a product can be described by the function p of x equals negative 0.4 x squared plus 280x minus 24,000, where x is the number of units produced and sold and p of x is the profit in dollars. Again, a word problem to start us out. So we're going to try to answer with words as we finish it. Part A, to maximize profit, how many units must be produced and sold? Maximize. As soon as I see that word maximize, I'm thinking vertex. Maximize, minimize, vertex, absolutely every single time. Okay, and I also check this. Since we have a quadratic, we know it's a parabola. Because the leading coefficient is negative, I know the parabola is facing downward. So it does have a vertex, a maximum. The vertex is a maximum. Using our formula, x equals negative b over 2a, again, to find the location of the vertex, we find that x equals negative 280 divided by 2 times a negative 0.4. Simplifies to negative 280 over negative 0.8. Pulling out a nice little calculator here, we get 350. To maximize this profit, we should produce and sell 350 units. Questions asked in words. Let's answer it in words. Part B, what is the maximum possible profit? Okay, so again, nice little how many units? We know exactly what our answer should be, 350 units. What's the maximum possible profit? Oh, we're now looking at the profit at the vertex. So I want to find the y-coordinate. And I answer it in the same way. All I'm going to do is substitute my 350 in for x, right, the number of units that we should sell to maximize. And I actually typed this out instead of just throwing it in a calculator and giving you an answer. This is a good check. If you are actually at the vertex, when you have ax squared plus bx plus c form, and you evaluate at the x-coordinate of the vertex, your first number here, the negative 49,000, should be exactly half of your second number, 98,000. So 49 is half of 98. And they should have opposite signs. If this is true, you know your answer is right up here, and you're pretty sure you're going to get the answer right here. All right, so the first number is exactly half of the second, and they have opposite signs. You know the x-coordinate of your vertex was right. It's nice to be able to reassure yourself along the way. And then when we add these, a negative 49,000 plus 98,000, the result will be the value of the smaller one, 49,000, the sign of the larger one. 98,000 minus 49,000 is 49,000. Subtract 24,000 from that, and we'll end up with 25,000. That's a great answer. If you get the answer 25,000, I'm super happy. But go back. What's the maximum possible profit? The maximum possible profit is, now I have correct units, the correct answer, my answer written as a sentence. Maybe if I put a period, it would be a better sentence, but I've answered in words as well. Producing and selling how many units will result in a profit of at least $9,000. Solve algebraically or graphically, and I'm going to use kind of a combination of both here. Producing and selling how many, it tells us to find x. All right. There we go. Producing and selling how many units? That says, hey, find your x value. Profit of at least 9,000, it tells us to set up an inequality. So we want our profit, big old profit function, at least. So 9,000 is the absolute smallest, so the pointy side at the smallest. We want our profit to be bigger than that, so we'll have a greater than or equal to inequality. So anytime we're dealing with quadratics, we always want to compare them to 0. We know the quadratic formula. We know that we could set it equal to 0, so we could solve the related equation, set equal to 0, and get 550 and 150. So at the x values of 550 and the x value of 150, we know this quadratic function is equal to 0. But we want it to be bigger. And this is where I use the graph. So here we have our 150. Here we have our 550. And we can see that's exactly where the parabola intersects the 9,000. So where is our quadratic greater than 9,000? It's between these two values. Between 150 and 550, the graph of the parabola is above the graph of 9,000. So in order to achieve our desired profit, we need to sell between 150 and 550 units. All right, I believe that's it for part 1 of 4 of the final exam review.